Welcome. If you're designing digital logic, you know that every extra state in a machine costs hardware resources. Overly complex state machines consume power, take up physical space on a chip, and slow down performance. To build efficient hardware, we have to simplify them. This table shows a complex, unoptimized state machine. Notice the sheer volume of rows here. We have 7 distinct states, labeled A through G, each with its own next state and output conditions. Storing all 7 of these requires a lot of overhead. To fix this, we use the Implication Table algorithm. It is a highly visual, deterministic tool that lets us systematically compress these states down to their absolute minimum number. Instead of trying to prove which states are exactly the same, we start by assuming everything is identical. Then we methodically hunt down and cross out the pairs that are definitively different. By following this process to the end, you guarantee the minimum hardware utilization. There is no guesswork or intuition required, just a strict process of elimination. This is the Implication Table grid, laid out in a staircase shape. On the x-axis, we list states A to F. On the y-axis, B to G. Each cell represents a pair of comparing states. Initially, we assume every pair is equivalent. Step 1 is phase 1, checking for immediate output conflicts. The rule here is strict. If 2 states produce different outputs for the exact same input, they are not equivalent. Comparing state D and E on our table. When input X equals 1, D outputs 1, while E outputs 0. Because these clash, they aren't equivalent, so we cross out the DE cell. We apply this exact same check to every pair on the board. This is the result of phase 1. All immediate output conflicts have been found and removed with these orange crossouts. The cells that survived this first pass share identical output behaviors. However, they require a deeper layer of logical scrutiny to prove they truly operate the same way. This brings us to phase 2. For the pairs that survived our initial check, their equivalency now depends entirely on whether their future behavior, their next states, are also equivalent. Isolating the A-B pair cell, let's map future dependencies. On input 0, A transitions to B and B to D. We log this B-D pair at the top. On input 1, A goes to C and B to F. We write CF beneath it. Applying that logic to the entire board gives us this populated table. Every single surviving cell is now filled with the specific next state pairs it depends on. The rule for phase 2 is this. A state pair is only equivalent if the sub-pairs listed inside its box are also valid. If those internal dependencies get crossed out, the main pair fails with them. Now we begin phase 3, iterative elimination. We have to scan the entire grid and check if any surviving cell is relying on a pair that we've already eliminated. Look at the EF pair in the bottom right. It relies on the CD pair. Following that dependency, we see CD was already crossed out. Because C and D aren't equivalent, E and F cannot be combined. Therefore, we cross out the EF cell. This creates a domino effect. With the EF cell dead, we find other cells depending on it. Scanning the grid, the CF and FG pairs both require EF. Since it's invalid, we eliminate CF and FG as well. The chain reaction continues upward. Because CF just fell, any cell relying on it is now invalid. That means the AB cell in the top left must also be crossed out. To ensure nothing is missed, you must repeatedly rescan the grid from left to right and top to bottom. You run this cycle over and over until a complete pass results in 0 new crossouts. This mathematically rigorous repetition leaves no room for error. It establishes logical certainty that the surviving states are truly equivalent. Once a pass yields no new information, the process is complete, leaving only a few surviving cells. We translate these remaining cells into explicit groupings. State A is equal to state D, and shown by connected dependencies, states C, E, and G are all equivalent. Let's bring back our original state transition table. This is the unoptimized 7-state system we started with. By merging those equivalent groups, we can consolidate the duplicate rows and rename the clusters to A' and C'. This is the finalized table, fully minimized to just 4 rows. A resource-heavy 7-state design has been mathematically compressed into an efficient 4-state system, ready to be built into hardware.
Thanks for watching. See you next time.